Hello everybody, let's talk about limits of trigonometric functions. Now for the most part, trigonometric functions are pretty well behaved kinds of functions, as we've seen from their graphs and as we've seen from some of the functions that we've dealt with. And the limit of trigonometric functions is pretty easy to follow. Basically, for each one of the cases, as you can see here, that if c is a real number and that number is in the domain of the trigonometric function, then the limit as x approaches that value c of any one of those 6 trigonometric functions will be equal to the value of the function at that point c. So for example right here, let's talk about this limit as x approaches 2 of the cosine of pi x over 3. Well, what we're really saying right here is that we're looking for a way to evaluate this, and if we look at number 2 on the list right here, we can see that if it's the kind of function where c is within the domain of the cosine of x, then the limit will be the cosine of c. Well, what is our domain for cosine except it's all real numbers, right? So in this case, we should be able to evaluate by a simple substitution of taking the cosine of pi times 2 divided by 3, which is to say the cosine of 2 pi over 3. Now, if you remember your angles, 2 pi over 3 is one of those quadrant 2 angles in which the reference angle, theta prime, is pi over 3, and we know that the cosine of angles like pi over 3 is 1/2. So we're in quadrant 2, we've got a value of 1/2, therefore this should be negative 1/2, and that is the value of our limit. And so for the most part, we really don't have too much trouble when it comes to trigonometric functions like this and looking for their limits. A real question for us might be is, well, when do these limits not exist, right? When should we be looking for when they do not exist? Well, let's take a function like the cotangent right here. A limit will not exist if one of the values from the left or the right doesn't exist of the function itself, if the values from the left or the right don't agree with one another, or if the value of the function oscillates as x approaches c. And we've got one here that meets basically all of those criteria. Let's talk about cotangent first. Cotangent of x is the kind of function that has a domain in which x cannot be equal to n pi, right? So we actually are talking about a value that is outside of the domain. Here's pi right here along my number line. We can see that that is a vertical asymptote. Well, we know that this is not going to exist, but we could put it a couple of different ways. We might say that if we were to attempt to take the limit as x approached pi from the left for cotangent of x, we can see that as we get closer and closer to pi in the x direction, this is the kind of function that's going to tend towards negative infinity. And what's more, the limit as x approaches pi, this time from the right hand side, we can see that as the x values approach pi, get it closer and closer to 3.14, from the right hand side, the y values tend towards positive infinity. Now, since the limit to the left is negative infinity, the limit to the right is positive infinity, the two values from the left and the right don't agree. As a matter of fact, they don't exist. And so we would have to say about this limit, it's the kind of limit that does not exist, DNE. All right, so that's one example where we have vertical asymptotes. Secant, cosecant, tangent, and cotangent are the kind of functions that do. But what about sine? Is there an occasion where that's true? Well, here's an interesting example. Let's say we're taking the limit as x approaches 0 of the function sine of 1 over x. What happens here? Well, I've done my graph here. I've written out my graph so that you can see sort of the behavior of this function. It's interesting because as x gets closer and closer to 0, both from the left and the right, the function tends to oscillate faster and faster. You can see that as x gets larger, the oscillations get larger, but as x gets smaller, the oscillations get faster and faster. Now this graph can't do it justice because as x gets smaller and smaller, look how all these lines are starting to bunch together, right? And especially you can see it right here, this curve, the oscillation gets very, very tight. And even if we were to zoom in on the graph, and let me do that right here, you can see that as my scale gets tighter and tighter right here, even though we are following more and more of these oscillations, they don't seem to slow up. And no matter how far we zoom in, we can see that that oscillation just continues to get worse and worse. So as we zoom into zero, look at what's happening right here. What could we say about that? Well, this is the kind of function in which our scale, regardless, is never going to approach. This is an example of a behavior that we say the function oscillates as x approaches c. And in this case, it's another example of a function whose value limit will not exist. All right, more to come.